Okay, I think we can start. Okay, so good afternoon, everyone. I'm Serena Graziosi. I'm an associate professor of the Department of Mechanical Engineering of Politecnico di Milano, and I am the chair for this second session on design for additive manufacturing. So let's continue after the session chaired by Tino Stanković. Let's continue the discussion on additive manufacturing, and in particular during this session, so we will have the pleasure to listen to very interesting presentation and also work papers. And I think that in this session, we have a very clear fil rouge, I would say, because we will start with Adam Mallalieu, who is a PhD student at the Chalmers University of Technology. And Adam will discuss about the lack of digital infrastructures in order to, we need to fill this gap in order to speed up the adoption of AM technologies in industries. And then we will move on, speaking again about the importance of knowledge formalization, which is very well related to the lack or somehow of digital infrastructure, digital tool, to speed up the adoption of AM technologies and the efficiency also of technologies, thanks to Giovanni Formentini, who is a PhD candidate at the University of Parma. And then we will put design for AM to the extremes in terms of personalization, thanks to the computational design approach developed by Tino Stanković and his colleagues from the Engineering Design Computer Laboratory of ETH, Zurich. And of course, I'm also honored to say that this paper, the paper from Tino and his co-author, won the Reviewer's Favorite Award. So congratulations from our side, from the audience. Okay, and then we will continue. So we have started speaking about big data, the management of a lot of data in order to reach, high level of customization possibility. And then we go on speaking about further data-driven approaches, because thanks to a computational model, we can also take into account the influence of the printing process, because in that case, in that paper from Karl Hilbig from the Technische Universität Braunschweig, I'm sorry for the wrong pronunciation, we will see how much the printing process influences the functionalities of our part when we speak about the possibility to 3D print heating elements as well. And last but not least, we will end the discussion with Patrick Müller. He is a research assistant at Leibniz University at Hanover, and this presentation will be about the use of density-based topology optimization method for optimize endoprosthesis. So again, it's about digital design solution, digital tools once again. So this is the end of the introduction, and I'm sure you will enjoy the presentation from our authors. So please, Philip.
Hello and welcome. My name is Adam Mallalieu. I'm a PhD student at Chalmers University of Technology, and I will be presenting the paper, The Role of Digital Infrastructure for Industrialization of Design for Additive Manufacturing, for the Design 2022 conference. This paper was written by me, Hajali, Professor Isaksson, and Associate Professor Massimo. The agenda for this presentation is the following. I will briefly introduce the background of this paper, the aim and the research questions, the research approach that was used in this study. I'll also present and discuss the results, which are also separated into two parts, a systematic literature review and an industrial use case. And I will finally wrap up with our final conclusions and recommendations. There's a lot of ongoing research related to AM, which is expected to be a critical technology for industrial competitiveness. One critical phase in the AM process is the design phase, which plays a big part in capturing the benefits of AM. Design for additive manufacturing, or DFAM, is a collective term for methods, tools, and guidelines which should utilize the opportunities of AM. There are, however, several challenges related to the industrialization of AM, and one of the identified challenges is the digital infrastructure. The process of DFAM is in particular considered to be digitally intense. For clarification of what is meant with a digital infrastructure, we define the digital infrastructure as to what comprises the information technologies used together to process the vast amount of data that is being generated, transferred, stored, and traced in the AM process steps. The following aim and scope was formulated, which is to review how the FAM methods and tools consider the digital infrastructure and identify a potential gap in literature, and to explore how the digital infrastructure affects the industrialization of AM. From these two research questions were formulated. First one being, in what way is the digital infrastructure considered in the FAM methods and tools, along with how does this then impact industrialization of AM? The study consisted of two parts, a systematic literature review aiming to address RQ1, along with an industrial use case with the intention to address RQ2. The systematic literature review was conducted using Scopus as the research database. A total of 209 publications were obtained using the final search string, which can be seen above. The publications are filtered through several steps, going from keyword filtering to abstract filtering and finally down towards reading the full paper. A total of 44 articles were reviewed and mapped to find potential gaps in the literature. 5 categories were used to highlight how the digital infrastructure is considered in literature. The first one is data format incompatibility. Methods and tools typically make use of different softwares, which results in a wide variety of data formats. It can become troublesome if the compatibility between the different formats in the methods and tools is not considered. 12 of the authors either considered the format being used in their own specific DFM method or tool or problematized it. The second one is information management. It is interpreted as the activity of managing information, including the transferring, storing, tracing, and retrieving information. The implementation of information management in DFM method and tools was only considered in 9 of the reviewed articles. The third one is data analysis, and it relates to the set of activities needed to understand and interpret data. This could also include what is often referred to as cleaning data. The need of cleaning or processing data generated by DFA methods and tools were seemingly neglected and was only mentioned by 7 authors in the reviewed literature. The fourth one is loss of information. Information can sometimes be lost either when transferring in between tools or during the use of one tool. The implication of loss of information either by a single or in between DFA methods and tools was considered about 10 times in the review literature. Tucker exemplified this when discussing the method for capturing geometries using 3D scanning. The mesh could not represent all geometrical features, meaning information could be lost on this step. The last one, data and information reuse, is to some extent related to information management, since it requires the ability to trace and transfer data. This category is more seen as an opportunity and refers to the knowledge that can be captured and exploited from the data and information that is generated by the DFA methods and tools. Only 3 authors considered the opportunity to reuse the data and information generated by the DFA methods and tools. The result from the literature review indicated that there is a low consideration of the digital infrastructure. Following the systematic literature review, an industrial use case was conducted together with a large OEM of construction equipment. The company seeks to investigate the potential of AM as an option to produce production tools used by operators on the assembly line. AM is particularly considered as an interesting option, since these tools are often produced in low volume and customized for operators. AM could then potentially reduce the lead time and cost of these tools. There is also an expectation that AM can increase the usability of the tools, if, for example, more likely designs can be produced. The purpose of the industrial use case in relation to this paper and study was more to explore how the digital infrastructure can impact the industrialization of AM. The case study consisted of performing a sequence of predefined activities. I do not have time to go through the procedure in detail, but we'll talk about the issues that were observed. The simplified digital infrastructure is visualized in the figure to the right. The performed DFM process was examined using the 5 categories used in the systematic review in order to explore the impact of this. And I will go through some of the observed issues. The issue of data formatting compatibility was observed in the case study. The output format from Fusion 360 is STL, and this format cannot be used to change the geometry in the CAD software. The output of the generated design instead had to be manually implemented on the original CAD file. Consideration of information management was deemed as important in the case study. The case study produced a large amount of data and information which both needed to be stored, communicated, and traced between different activities. An example of this was the requirements needed in the FEM analysis, which is illustrated in the top line. Data analysis was needed in the case study, since some of the generated data or information had to be processed before entering the next step. The output from the generated design was not only delivered in a non-compatible format, but it also required manual cleaning to ensure that the proposed design could be printed. Loss of information was also observed in the case study. The optimized design had to be translated in the general guidance for the design. This resulted in information loss, since some aspects of the optimized geometry were not possible to replicate. There were some identified possibilities for data and information reuse in the case study. An example of this was the produced print data. illustrated in the dashed line. It was possible to make use of it to find ways of optimizing the print settings, and this could potentially be reused for future prints. So to summarize, the observed issue seemingly influenced the DFM process, making it less effective and efficient. The goal of the case study was to make the tools more lightweight, and this was limited by the digital infrastructure, thus making the DFM process ineffective. An additional goal was to make the tool time and cost efficient. This was also limited by the digital infrastructure, thus making the DFM process inefficient. This could potentially have a negative impact and effect on the industrialization of AI. Relating back to the aim of this paper, which was to review how the design for additive manufacturing methods and tools consider the digital infrastructure and identify potential gap in the literature, and to explore how the digital infrastructure affects the industrialization of additive manufacturing. Can conclude that there is a low consideration in the reviewed literature indicating a gap. In turn, this can have a negative impact on the industrialization of AM as well. We therefore recommend that there should be more consideration of the issues raised in this paper when developing and validating DFAM methods and tools. We also believe that the digital infrastructure needs to be studied further to strengthen our arguments. Having said that, I would like to thank you for listening.
Good morning, everybody. I'm Giovanni Formentini, and today I'm going to present our work entitled A Framework to Collect and Reuse Engineering Knowledge in the Context of Design for Additive Manufacturing. During the presentation, we'll see the research context on the go, the state of the art, what we have done, the case study, and conclusions. The research context in which we're working is the development of additive manufacturing technologies. Additive manufacturing is a fast developing technology, but right now there is a lack of tools to collect knowledge in order to avoid manufacturing issues during the product design. So our goal is to create a framework in order to collect design action for design for additive manufacturing technologies, which are based on ontology in order to consider and anticipate manufacturing issues during the product design, and also to consider and select the best printing direction according to the requirement. Currently, in literature, there are some sources in which it's possible to get information for designing for additive manufacturing. However, this information are limited and not structured. Moreover, the knowledge framework that has been developed for other technologies cannot be used for additive manufacturing technologies. Finally, there are some preliminary models to formalize the additive manufacturing knowledge, but these models are lacking of manufacturing problem consideration. So what is missing right now is a framework able to collect design action that can be applied during the product development and can anticipate manufacturing problems, considering also the printing directions. The method that we are proposing is composed of 3 steps. The first one is a literature analysis, then there is an ontology definition, and finally the design for additive manufacturing guidelines classification. The first step, the literature analysis, was performed by looking at information inside sources like books, scientific database, company database, and so on. The research was performed using a keyword approach, and we use keywords such as design rules, design limitation, design expertise, and also synonyms. Moreover, to further widen the research, we did brainstorming session with experts in the field of additive manufacturing in order to collect their knowledge. The second step is the definition of the ontology. When designing a product that has to be manufactured with additive manufacturing technologies, several parameters must be considered. For instance, the technology that is used, the material, and even the feature that must be created need to be considered by designers in order to anticipate manufacturing problems. Following this, we create an ontology based on 3 domains. The first domain, that is called domain 1, describes the geometric features such as holes, walls, surfaces, and so on. The second domain, called domain 2, is considering the classification of additive manufacturing technologies. This classification has been done based on a funnel of 4 elements. The final domain, which is domain 3, it considers the material that has to be used. In particular, we developed the ontology for considering materials such as plastic and metals. The ontology, moreover, defines a clear structure in order to build design guidelines. The structure of a design guideline must follow the form of verb plus noun and also must have a mathematical threshold associated with the design guideline. The threshold is used to understand if this design guideline is respected by features or not. We do have three different types of errors. The first one is an information error. It means that the design guideline is not respected, but this won't impact the manufacturing properties of the product. The second one is a warning. It means that the manufacturing process can be still done, but the cost and the time of the process is increased. Finally, we have a critical error, which means that the manufacturing process will fail if the feature won't be fixed. The final step is the classification of design guidelines, and during the classification, the design guidelines were clustered into two databases. In particular, one is called Additive Manufacturing Design Database, and it collects design guidelines to be considered during the product design, while the other one is the Additive Manufacturing Machine Operator Database, and it collects design guidelines to be considered during the manufacturing process. The proposed method has been applied to two different case studies. The first one is the stereolithography additive manufacturing technology, and the component which we analyzed was the body of a toy car. In this specific case, the printing directions are not mandatory, and the most important feature to respect is the aesthetic requirements. Using the machine operator database, it was possible to identify the best printing direction in order to maximize the aesthetic requirement. In this case, the printing direction is the one shown on the right hand of the slide. Then, using the design database, it was possible to see that 52 features were not satisfying the following design guidelines that you can see on the right side. Due to the time constraint, we're going to show you just one design guideline, which is the AMP 119, which is suggesting to avoid embossed detail with a height lower than 0.5 millimeters. As you can see on the picture, before the modification, the feature was in error. Then we modified that, increasing the height, and everything was fine. The second case study is a connecting rod. In this case, we do not have a mandatory printing direction as well. And the most important characteristics are the mechanical performances. Using the machine operator database, it was possible to identify the best printing direction in order to maximize the mechanical performances. And then, using the design database, it was possible to see that 27 features were not satisfying the following design guidelines, the one that you see here. For example, the design guideline AMM001, it's suggesting to avoid sharp edges. And as you can see on the right side, we do have the before modification representation and the post modification representation. In conclusion, the ontology and the framework that we propose help designers to spot errors during the design process. However, it's difficult to abstract design guidelines and translate them according to the developed ontology. Moreover, additive manufacturing knowledge is still limited and continuously evolving, so there is a need of constant update. Future development will focus on increase the database and also on automatize the retrieve of CAD feature to reduce the analysis time. Thank you for your attention.
Good afternoon. My name is Tino Stanković. I'm a senior scientist at Engineering Design and Computing Laboratory at ETH Zurich, Switzerland, and I'm going to present you our work on computational design of an additively manufactured origami-based hand Orthosis. I would like to start off by presenting the motivation for our work. In recent years, a significant number of new additively manufactured hand Orthosis designs are being reported. Those designs, in comparison to the conventional casts, are lightweight, better ventilated, can be easily removed, don't have excessive pressure point. So there are many advantages. However, there are also disadvantages. They have to be post-processed to remove sharp edges, for example, and to remove the support structures. And our motivation comes from the drawbacks in which we try to design an origami-based hand Orthosis design that can be, of course, produced flat and then folded to a person's arms. The openings can be easily added, and some other features can be of origami patterns that I'm going to discuss in future slides can be beneficial to realize such a design. We reviewed several crease patterns that could be good starting points for our design. All of those patterns have been used to approximate shapes in work from different people, right? So we narrowed our selection to Yoshimura-based patterns in contrast to for instance, water bomb-based patterns, or for instance, Miura-Ori patterns shown in A and B, because it's known that Yoshimura-based patterns, once they fold in a column, create a rigid column, which is actually beneficial for a design of hand orthosis. Out of different versions of Yoshimura-based patterns, we decided to go to the simplest solution, which is shown in C. And if you compare C and E, you can see that the degree of freedom of each vertex is higher in the C, because it has 6 crease patterns intersecting with each vertex, in comparison to E, where there is only 4. So we go for more design of freedom, which will allow us to explore the third space more. With respect to the embodiment, we decided 2 different strategies, right? Between 2 different strategies. So A shows a strategy in which rigid material is connected by a flexible membrane, whereas B shows rigid material being connected by compliant or flexible material. So B is beneficial for our case because A introduced a reduction in stiffness, right, due to the gaps between the rigid material. So we decided to embody our design using B. The methodology that we can develop for our work involves 3 phases. So the data acquisition, surface approximation, hand orthosis, crease pattern design, and embodiment and fabrication. Of course, since we needed to set the parameter settings and find the design heuristics, we iterated between the phases and not only discovered designs, but also try to pinpoint design parameters and relevant design heuristics required to produce such designs. Let's describe the phases in brief. So phase 1, the data acquisition and surface approximation. First, in A, cut off parts of the point cloud that have been scanned that are not interested for us, and B shows what happens with the remainder. So at each elevation, we approximate the point cloud with an ellipse, right, which is effectively a surface approximation total. In terms of C, theta, A, and B. The question is, out of those 45 ellipses that we have in C, and effectively in set E, which of those ellipses should I select when I design a Yoshimura pattern for each basis? So I can't use all of them, right? In phase 2, we can show the crease pattern design, right? Whereas A shows the Yoshimura pattern, a generic one, the image in B shows the situation that we have. So for each ellipse, we approximate ellipse with an envelope of polygons constituting the pattern, right? So the question is how to solve this. And we solve it as an optimization problem in which a summation of the surface area surrounding each ellipse is minimized, right? In terms of angles phi. The question, of course, is which is appropriate polygon degree to actually produce feasible designs, which is the tolerance of length, so how short should be the faces, and also the tolerance of developability. So the conditions for developability or in this particular case, flat foldability of almost flat foldability of the crease pattern is the summation of the sector angles for each internal vertex is 360 degrees. So this is also included in the optimization. In the embodiment stage, we have first the addition of the overlapping patch for fixation, shown in blue in figure A, post-processing for the hole for the finger, and finally, when we manufacture using PolyJet multi-material 3D object 500 Connex, we do it so that the zero thickness line is in contact with the arm, and for the rigid material, we use Vero White Plus, whereas the complete material is Agelus 30 Black. Results for the surface approximation are actually very good. Image A shows 4 different ellipses at different heights, right? And B shows the mean runtime of 6.5 seconds. So this is not really a problem to solve using optimization. The designs of the design space is actually a bit more complex. So what we did, we tested for different parameter settings ranging for 5 to 7 polygon degrees, right? 5, 6, or 7. And different number of ellipses involved, ranging from 5 to 8, right? In total, we exhaustively enumerated 36,876 designs with a mean runtime of 35 seconds. Empirically, using testing, we somehow decided to filter the design space and decided the mean violation of developability and mean violation of length boundary should be 1 and 0.5 respectively. This gives us image B with in total 632 designs, out of which 495 designs with 5 cuts produce different types of artifacts like spikes or twists. And then we rule them out, and the remaining 143 designs with 6 and 7 cuts respectively were manually filtered. In the end, takes us to select the design shown and insert D1. Also, you can see that the search space shows the behavior that if you are closer to actually satisfying the violations, the designs could be worse than the one that we selected. That means that more work is required to tune our optimization formulation. In the end, we produced a design shown here. It took 1 hour, 46 minutes to print, and it weighed 237 grams. To sum it up and conclude, we demonstrated how origami principle can be used to design hand Orthoses. We showed the benefits of Yoshimura pattern. We showed computational process, how to do it, right? Of course, the exhaustive search is obstacle and requires more work and automation or even interactive design selection procedure. And we also showed that the better designs, in our case, at the moment feature high number of cuts, ellipses distributed equidistantly, and low polygon degree numbers. This is it. Thank you for your time. I would be more than happy to answer the questions.
My name is Karl Hilbig. I'm a research associate at the Institute for Engineering Design of the Technische Universität Braunschweig. In the following presentation, I would like to give you an insight in the conference paper, Data-Driven Design Support for Additively Manufactured Heating Elements. The agenda of this presentation is linked to the method of the paper itself. In the introduction, I would like to give you a motivation and possible areas of applications for these functional structures. The experimental setup contains the design of experiment, the specimen design, and the applied measuring method. In order to use the experimental data for the product engineering, a software tool was developed. The tool uses a data-driven design approach to compare possible process parameters with their heat distribution. Therefore, the workflow and the modules will be explained. The brief presentation will last sum up the carried out work and will give to you upcoming research fields. The research motivation of this investigation is based on the freedom in product or part design by additive manufacturing. Especially the multi-material design of additive manufacturing allows a combination of multiple materials in one part. Functional polymers can integrate additional functions like heat-generating structures in the product design. The goal of this research was to support the product developer with experimental data for the integration of homogeneous heat structures in the end product. Possible areas of application can be seen in the function of interior heating, de-icing of wing surfaces, or temperature stabilization of products. In the following slide, I will present to you the hidden agenda of the specimens. All specimens were manufactured with a process material extrusion by the product plant tool changer from E3D. The characterized material was a filament Blackmagic 3D conductive which has electrical conductive properties. For the design of experiment, a D-optimal design space with a quadratic scale function with 2 input factors were used. The input factors were the printing temperature and the raster angle of the part orientation. The measurement configuration consists of a source meter and a terminal imaging camera. The main function of this rack was the repeatable and automated measurement of the specimen heat distribution at different voltage levels. The source meter was to source and sense the voltage and the current of the specimen. The camera recorded the resulting heat distribution on the specimen surface. On the right side of the slide is an example overlay of the heat distribution on the specimen surface. For the measurement of the voltage-depending heat distribution due to self-heating, the parameter sets were observed. The following process steps were performed automatically. At the start of the measurement, 10 volts were applied on the specimens. Through the Joule's effect, the specimens heats up to a stationary condition where the supplied electrical energy corresponds to the dissipated heat flow. If the stationary condition was reached, 100 measurements were made at a constant surface temperature. After the temperature rise, a terminal image of the heat distribution was taken and the voltage was increased with 1 volt. The figure shows a characteristic heating behavior of the specimen, where the input voltage has an incremental rise and the surface temperature reaches at each level a stationary condition. To enable the use of the experimental data in the product development process, I will now present the workflow in the support tool. The architecture of the data-driven design support tool is based in 2 core modules. The first module is a surrogate module, where the experimental data is transferred to a regression model. The defined input factors correspond with the parameters of the design and experiment, the voltage level, and the heat distribution of the experiment. The implemented method allows an inverse parameter identification for the process parameters. By this, we are able to predict process parameter sets that lead to a selected electrical properties and thermal distribution of heating panels. The second module is the classification module. The classification module is an image classification with the convolutional neural network. In this figure, you can see the results for the classification of the thermal images. It shows 8 clusters of the similarities in the output factors of the heat distribution. The cluster 1 and 2 represent a homogeneous heat distribution. Cluster 3 to 8 show an inhomogeneous heat distribution over all specimen surfaces. With this module, we are capable to support the product developer in the area of the prediction of feasible process parameter sets by the heat distribution. In conclusion of this research, we additively manufactured heating structures, characterized them, and the knowledge was redefined for product development using a data-driven design approach. This enables a fast screening of the design space for future product development, and for future process parameter sets, the temperature distribution can be predicted. The upcoming research fields can be divided into 2 areas. The first area is a shape variation. We would like to change the geometry first to complex planar forms and then to 3-dimensional surfaces. The second field will be the integration of a design checker by extending the tool with a shape segmentation algorithm. I hope that I could give you an insight into our publication and that I could interest you in this research topic. Thank you for your attention.
Hello, dear colleagues. My name is Patrick Müller, and I'm a research assistant at the Institute of Product Development at the Leibniz University of Hannover. I would like to thank you for the opportunity to present my research results here. Today, I would like to present the paper I wrote together with Dr. Paul Gębarski and Professor Roland Lachmeier. This is entitled Density-Based Topology Optimization for a Defined External State of Stress in Individualized Endoprosthesis. Or more simply, how do graded data structures make osseointegrative implants better? To begin, I would like to briefly introduce the 2 domains in which we are located here. On the one hand, there's arthroplasty, which is experiencing considerable growth in Europe, also due to demographic change. Approximately 450,000 people in Germany needed an artificial joint replacement in 2020, mainly knees and hips. But all other endoprothesis implantations are also growing steadily because people are getting older and more demanding with regard to their environment and themselves. Of this 450,000, a total of 50,000 are revisions. And it is shown that the numbers of revisions are highly increasing. One of the main reasons for revision is adaptive loosening due to stress shielding. In stress shielding, due to the significantly higher elastic modulus of the implant material compared to the bone, there is a shielding of the mechanical loads in the bone, which leads to increased bone resorption and reduction of bone density. With exactly this problem, we now open the second domain of this work, additive manufacturing. Advances in additive manufacturing enables grading, for example, through lattice structures. This leads to one of the main advantages which we are used here in this work, the local adjustment of component properties. If we now bring both areas together, we can specify the main question of this work mentioned at the beginning and let it become, how can implants with graded lattice structures help to reduce the numbers of revisions? To be able to answer the question, we need to take another look at the effect of stress shielding and understand what impact the implant actually has on the bone from a mechanical point of view. All of the following slides refer to the example of hip endoprothesis, but are analogously transferable to all other osseointegrative implications, such as knee, shoulder, or even exoprothesis. A numerical static simulation of everyday movements shows in the upper part of the image a relatively homogeneous stress application in the entire medial region of the femur in the preoperative state. After a conventionally manufactured implant has been virtually implanted in the lower part of the image, and the same movement has been simulated, a clear decrease of these stresses and the mentioned red area shown by the blue coloring can be seen. This shielding is the so-called stress shielding effect. The aim of the optimization, the topology of the implant should be therefore be to maintain the stresses in this area of the bone or to make them as great as they were before the operation. Our approach attempts to map precisely this undertaking. A method for density-based topology optimization for a defined external state of stress in individualized endoprothesis requires two models. The first is a preoperative model of the femur alone, the so-called target state, on which information about the physiological stress state in the bone is numerically recorded and stored. The postoperative stress state with a full implant is recorded in the same way and compared with the target state. Now, the density field of the implant is optimized until the actual state corresponds maximally with the target state. For this reason, we also call the method a method for creating osseointegrative implants that are not noticed by the surrounding bone from a mechanical point of view. The base is the individualized implant. This implant is divided into two parts, a boundary layer, which is constant graded, and the inner part, which is optimized. To achieve constant pore size at the outside from maximum bone ingrowth, the marginal density was set to 40% at the outside. The inner region was homogenized using the Ashby-Gibson model, which established the relationship between the elastic modulus, density, and the respective lattice cell. The fact that the optimization leads to new, better stress distributions in the bone is shown here. Here are the stress differences between before and after the operation for each volume element. Again, as a reminder, the closer this difference is to zero, the better the result, and the more the stresses after surgery correspond to the physiological stress of state before surgery. This procedure reduced the stress difference globally by 42%. Now we have an optimized density field, but not yet a ready-made implant. Only in this step, by using graded laser structures, a manufacturer implant becomes out of the optimization. To recreate this, the original geometry from the implant again serves as output. This volume is voxelarized and filled with small cubes. In each of this cube, a unit cell with optimized density will be placed later. Body-centered lattice structures are used because they can be printed without manufacturing restrictions and are easily customizable due to the struts. Here is the grading of the optimization just shown for an individual implant. It can also be seen here that the optimization tends to produce small islands of the material. At this point, I already come to the summary and the outlook. In the last few minutes, I have presented a method for determining an optimized density topology for endoprosthesis using lattice structures for all bone in cord implants. The numerical investigation shows a considerable potential of this approach, especially since the topology optimization results are manufacturable and implanted by coupling with additive manufacturing. Therefore, the next steps should be definitely addresses experimental validation. These are relevant to underscore the positive outcomes of this method. With that, I would like to thank you for your attention, wish you good health, and look forward to your questions.
Okay, here we are. Thank you very much for the very nice and very clear presentation. I think all of us enjoyed them. So now it's time for questions. I've seen that also the other presenters were quite active in asking questions, so which is really good. It seems there are clear commonalities among the papers. But also we have our moderator who has asked questions. So my invitation is to unmute yourself and ask a question directly. We want to see you, Philip.
Okay, thank you, Serena. So first of all, thanks for all the wonderful presentation. The first question is for Adam regarding your loss of information. I'm interested, did you find in your literature review or somewhere else, what are the most common type of information lost during this process? And can you give me an example, what is, for example, a critical information loss that we really should avoid? Yeah, and I have one more question for you as well. I saw later in the presentation that you use both Fusion 360 and V5, CATIA V5 in your case study. Why switch software? Shouldn't it be better to stick just with Fusion 360?
Yes, thank you for the question. The first one I will start to address. And first I can say to the first part of that question, I don't think I can say what is the most common because we only had 10 examples. So I won't be able to sort of conclude what is the most common, but I can of course provide some examples. So I would say that there were different kinds of loss of information. And that of course depends on the method or tool itself. What is the purpose of the method or tool? Because they're different, they can either be sort of try to help with the system support, generate designs, or just generate some type of knowledge. But the examples that we saw that were mentioned is, for example, meshing itself. It's a way to approximate things. And if you do this in an appropriate way, of course, it's going to sort of remove some type of information. And this was also related to scanning, where the scanning approach itself could miss out on certain features. And if you don't consider this when you develop the method and sort of in a clear way state that to the end user that this is something you need to consider, there's a risk of losing some type of information. And then, of course, depending on what the expected output or the sort of desired output, it will depend on how critical it is. Another example is also going from CAD to STL. Here you cut some modeling knowledge. You're not able to sort of make changes geometrically in the STL file. So here automatically you remove some information, parameterization and all kinds of things. And actually another fun thing that we realized, I'll see if I can find, if you hold on for a minute.
We have a real-time show. What? That's cool.
This is a broken lifting tool, but it was like that before. And actually, what we didn't think about what was when we printed this, we didn't change the resolution on in CATIA. So there are some sort of weird curvatures. And that is also, of course, some type of loss of information where due to the digital setting, going from virtual to reality, you can lose some information. And another example would also be then more in terms of knowledge, where in the example we had, we got requirements in the form of a PDF, and then we interpreted those. And to our own ability to actually be able to tell, okay, what are we supposed to do? We sort of did it in a wrong way and made a design that was not flawless, so to say. And also regarding the optimization output, we made the transferring sort of manually because we are not. I'm not an expert in the topology optimization tool itself, And I know that you can clean surfaces and so on, but you cannot exactly extract the complete topology optimized structure every time. So I had to sort of manually interpret the sort of features that were, and then insert them into my own design in the 2D drawing feature in CATIA. So there instead, I lost some sort of knowledge or information in what could be the sort of optimal design by my own ability to actually transfer that result. So that was an example of that.
Okay, great. Thank you very much.
So thank you both. And now there is also a question from Giovanni. Actually, it was also my question. So, but please ask.
Go ahead.
No, it's my pleasure. No, Giovanni, it's nice that we had the same idea in mind. Yeah, please.
Yeah, so thank you, Adam, for the presentation, of course. It was really nice. And actually, my question might seem like a little bit dumb, I'll say, let's put it this way. But as I said, digital infrastructure, to me, it's a very, very broad term, and that's fine. So I was wondering, what do you mean by digital infrastructure? And as I said, maybe you already explained that in the presentation. If so, pardon me, I just missed that.
Thank you for the question. And I understand your sort of question as well, because I think it's equally troublesome to try to define it, because it can be so broad. But as we try to define it, I usually use a sort of process-oriented view, where I see that whenever you do some type of design or whatever, you go through different process steps. These steps are then called activities, and these activities are then making use of different methods and tools. So within this sort of process, there is some type of knowledge, information that is being transferred from step by step. And this is enabled by also making use of different tools. So for example, when we use Fusion 360, that's one type of tool, one type of software that will create a different type of output and be dependent on different type of input. That information that is then digital is supposed to be transferred into another tool. And I need to have some sort of sense or idea of what information is being sort of flown in this process in order to better understand how should I sort of make use of my tool and adapt it in sort of relation to different standards or different formats for it to function properly. Yeah. Because if I do not consider it in the right way, I will perhaps create some output that sort of goes out in the blue, because there's no way of actually transferring that output as input into the next step.
I see.
If that clarifies. So it's basically the sort of overall structure of steps and activities that makes use of different methods and tools.
Yeah,
where you then will have a format, information, etc., etc.
I see.
So it can be quite
clear. But so I'm just big backing on this question actually. Are you considering this from a broad point of view, right? So you're not doing that just for a specific technology. You're trying to find, let's say, a definition, a method for whole technologies, right? Kinda. I mean, that's your.
I would say the way that we are working in the project is trying to follow standards, and then from my end, my research topic is more about utilization of research methods and tools for design. And here I see it as a future limitation that if you don't consider these aspects, for example, it will limit the industry's ability to utilize the method and tool itself. So I'm not entirely sure whether I will come up with guidelines or recommendations or whatever that could be. But this is one aspect that sort of needs to be considered. And the earlier you as a researcher account for this, I would say the higher the chance is for industry to adopt it. So that is also why we include industrialization point of view, because there is one sort of thing being in a very research context, and there's another thing being in more an applied context where you might have less time. So for example, talking about data analysis, being a researcher, we have several hours to sort of process the data. But if you're a designer, and in this case specifically a tool designer, they usually have let's say 6 to 8 hours in lead time to make the design of the tool. So they wouldn't really have the ability to process all this type of data. But of course, it depends on the context itself. But we want to make this problem surface. So we have at least thought about it when we develop the methods and tools. Yeah, and I would say one recommendation for that is try to think for yourself, okay, how could my tool be used in a sort of an automated workflow? Where will there be sort of disruptions? Because there is a good idea to understand where there is some type of breakpoints, where there is a gap in that perspective.
No, makes sense. Thanks for the answer.
Thank you for the question. Yeah.
Yes, thank you both. Actually, also in my mind, when speaking about infrastructure, was also curious to know about software and hardware infrastructure, both because, as for example, we have seen, or we see in the paper of Tino, for when you need lots of computational resources, you need also something that supports you on this kind of activities. That's extremely important. And also for the knowledge and exchange, for the information exchange. And actually now we move to Giovanni again, because I think these two papers are very well connected, I would say. I think all of them are very well connected from certain point of view. And actually there is a question from Philip again, and then I will ask mine.
Okay, thank you, Serena. So, Giovanni, very interesting paper and topic. I was working on something similar in my PhD. So, one challenge that I faced is when you try to define design guideline or design principle, design heuristic, whatever, however we call it. First of all, how did you derive those guidelines, and did you use some predefined vocabulary for defining it? Because, for example, I saw in your presentation, in your paper, you have to avoid sharp edges. What if somebody wrote to avoid sharp lines or to avoid sharp points? How will your ontology cope with this semantics in your approach?
Yeah, that's actually a really good question, because that was one of the main challenges that we had, of course, because basically to keep it in a really, really high level, the problem was, how do I translate human language into a computational one? Basically, that was the question. So what we did was, first of all, we did the literature review, and as I said, so let's get how we do that with blood. Basically, we spent tons of hours reading stuff, looking for stuff, basically. And the method that we used was easy. Basically, we kept everything in an Excel file, and then we were reading that stuff, translating into some words that we predefined. Like, as you said, we said if we have lines, okay, for us it's a edge. So we just translate all that stuff and we create this database, basically, in which everything is how can I say, everything is expressed according to that sort of vocabulary that we made. Of course, this is what we did. And let's say if you want to use our vocabulary, our database, you need to know what kind of vocabulary we're using. Otherwise, you look for lines, but there won't be any lines because they're just sharp. And that's let's say how we made the approach. But as you said, it was really, really tough because some guidelines were really, really generic. And the main problem was, how do we find a mathematical parameter to link to a specific guideline? So let's say avoid sharp edges. The next question would be like, okay, so let's say avoid lines and sharp edges. So next question would be, what is a sharp edge, right? So we had to dig into the literature to understand what was the meaning of sharp edge. And actually we found out the sharp edge is changing according to the technology you're using. And now I'm relating to the Adam paper. And that's why I asked this question at first to Adam, because for our case, everything is changing according to the technology you're considering, the material you're considering, and that's the toughest part ever. And I put that as a drawback in our work, because it's a very, very fast changing landscape. So basically, we did a ontology that maybe is not working anymore, because you need to keep up with the technology. Resolution is higher. Maybe what was a sharp edge yesterday is not a sharp edge anymore, right? Let's say the cool thing about this ontology is actually that you can link this ontology to a CAD program, and while you are modeling, you can run an analysis, and it will spot you the error. So right now we haven't do that. We just spot the errors physically. So we picked, as you saw from the presentation, we picked 2 case studies, and we said, okay, let's measure this stuff. This is will let's say fail this design guideline, so we're gonna fix it. But the cool thing is that with this database and with this ontology, you can automatize this stuff. So basically, while you are designing, and getting back on Adam topic, if I remember well, he said that he had a problem while he designed an object because you didn't change resolution, right? If I remember well. That was basically a design problem. That if you had something like an ontology in a database like we are trying to build, you could have avoided. like saving money, resources, and stuff like that.
Yeah.
I don't know if I
Very interesting topic. Thank you very much for clarification.
Yeah,
Yes,
thank you.
Thank you very much, Giovanni. I have a question, but I need also a quick answer because otherwise we have not enough time. No matter
Yeah, sure,
all these
sure,
topics
yeah.
are very interesting, so it's a pity not to have enough time to discuss them. My question is about this. You spoke about human language. I really like the idea that you have two databases. The second one related to the operator. And they have all the knowledge related to the 3D printing of stuff, the operators. Can the database learn from them somehow in the future? Maybe in the future.
Automatically,
Okay.
Okay. Everything is possible, right? So I think it will be possible. If you ask me how, I don't know yet, but I think it will be possible. Yeah, for sure. Yeah.
Thank you very much for being very quick about now the stage is again yours because you have a question for Tino Stanković. So please.
Yeah. So first of all, yeah, I really love the piece change. It was really funny. So it was great. Apart from that, my question is quite simple. As I said, the presentation was quite clear, method as well, and everything is clear. It's just a curiosity. Why a hand orthosis? I mean, you think might be actually an actual product that people would like to buy or use, or you just pick that because I don't know, like you are an expert on that, so you say.
I think that we had. Thank you for the question, and it was I mean, it's always funny when you hear yourself talking, right? After 2 years, it's the same, right? And I had to say a lot, and so I had to compress it in 7 minutes. And
it was great.
I wanted to say, I mean, it's both kind of, right? We were thinking about origami because we do also research in computational origami, and then said, why not trying do something with hand orthosis? And also hand orthosis came as a part of something that was on site because I was in a negotiation for a certain project and I had hand surgeons involved, right? And then it's all about these things, right? But they did not participate in the paper, right? And then we said, why don't we try it? And it also looks cool, right? And this is where the ended, because that wouldn't be the first time origami made its way, or something that looks like origami made its way in a high fashion, let's say, right? Because we know the handbags for, say, Miyake, you can see they look like origami, but they don't have any functional value there, right? Except being really cool, right? So
it reminds me of famous handbag. So
yeah, it's from Isai Miyake, and now we advertise him, right? But okay, he will say thank you. I think, and in this particular case, our patterns also carry loads, right? So there is a distinction there because they're also functional. And we thought it was a cool project, and it turned out to be much more work than we anticipated. Also, in the end, and also, I mean, it's far from, I would say, medical application, right? Because there are many points there are missing, right? I mean, we use the cluster, okay? All of these things should be brought to a smaller scale, right? For a physician to use it fastly, need to improve the optimization so that you get results more precise. So there is many elements there. But yeah, origami are cool. They are coming to design. Design methods are being developed. Much is still unknown, right? Especially when you thicken them and put the real materials and get the real behavior, then things become really difficult, right? So it's a very vibrant research area.
No, thank you for the answer. It was just really a curiosity because, as you said, we all know how it works. I was just curious if you also thought
it
about
looks cool, right?
Once
on your hand,
no, it's great.
This
actually,
is nice,
it's great.
right? I mean, so yeah.
Fair enough. Thank you very much for the answers.
I have a quick question, sorry, for you about the AM technology, because you said, I mean, now you have this powerful approach, I would say, but what you are missing is the 3D printing technology, which is a pity. I mean, because you mentioned in the paper that, of course, you use multi-material stratasys technologies, but you, if I'm not wrong, you had some issues in the flexible material somehow. So how far we are from this point of view in order to allow this kind of complex
Serena, it depends how you some people say issues, some say opportunities.
Yes, you're right.
Once you have a crease pattern that's realized as a in this form where you actually can print multi-materials, right? Then you have rigid faces and compliant hinges, right? And that's great, right? Because the pattern that we did is actually not completely deployable because it does not work. So there are some, constraints that are not satisfied to the degree that it will be actually flat in the end. But since the degrees of free are many rather than one, depending on the behavior of elastic material, then you can actually deploy something that's normally not deployable, right? So in that sense, someone would say these are hidden degrees of freedom. The others would say these are parasitic degrees of freedom, right? Because sometimes you don't want them, right? You would design a nice mechanical device that's origami-based and deploys, and then you say, okay, it has 2 degrees of freedom, but the reality it has 7 or 10 or hundreds, right? Because of how you did it. So people did other stuff, right? You can do it, of course, with hinges that are developed differently, right? But then it's mechanical design, it becomes a little difficult, and then it loses sort of the beauty. But in respect to the general design, I think there are still lots of steps that need to be done, because only recently, right, because we are developing lots of methods that actually do the zero thickness model, so you have kinematic behavior, right? But once you put the real materials, then the range of motion changes, then the kinematic material is the kinematic behavior is also sometimes, most of the times, not preserved, right? So you have different benefits, depends on how you actually thicken, right? And which principle for thickening you use, right? And when you have all of that, and you have multiple patterns, people did research, so you can see, for instance, there are band gaps in kinematic behavior. They actually tell you which pattern would deploy or not deploy at all, or will deploy easily or more complicated. And all of these things are important for mechanical applications, but there are still, there's a certain paper coming out with a certain pattern analyzing that for certain configurations. So we are far from a generic principles, right, in which we would say, do this, do that, right? But there is progress, right?
I'm sure there is progress, I'm sure. Thank you, Tino. Thank you for the very interesting work also in your case, and again, congratulations for the award. Okay. So now let's move to Karl. Wow, Karl, my first question is, how many samples did you have to print in order to create this model and to fit this model?
We printed about 160 samples with 3 specimens per each, so quite a lot. So yeah, but it worked quite well.
Yes, I seen. Indeed, my further question is, you of course you started from samples. So do you think that then this model can be extended and can be used when I have to print larger part, for example, like those complex forms or 3D and so on?
At that stage of this work, not. But it will. Now the paper is almost 6 months ago. We had just flat surfaces, and now we changed with small features like holes or triangles with it, and it's also it's also can go with this model. We first started with the changing of process parameters because we used the MAX, it also calls fused deposition modeling. You can you have a high influence in the electrical properties by the properties of the process itself, like the printing temperature, the printing speed, but you have quite higher influences by the path orientation, like how the passes go through your go through your design or through your panel. And now we are making our own slicer so that we can slice or change those paths through the connecting points. So I think, or I hope in the next few years,
I will able to print complex forms with features, holes, and the different kinds of stuff that we can use those elements in automotive or other stuff.
Okay. Thank you. And okay, I have another question for you, which is related to the one of the next step of your study, which I think is also extremely interesting, in a way that this model can support also material design activities, so material development, which means that this model in the future could somehow provide some insight on how to tune the, for example, PLA characteristics or the matrix characteristics in order to improve the efficiency of the material, for example.
The algorithm or the whole work is linked to just one material. So actually, I don't think that you can easily switch the material. At the moment, there are just a few polymers on the market who have those possible properties.
Okay.
Most of them have properties that allows just to have an inhomogeneous heat distribution over the panel. So further researches will link to this, but it will be very hard.
Okay. No, I understand. I asked this question because I love material design. So that was my curiosity. I've never tried this kind of conductive filament, but in the near future, I will for sure.
Oh, thank you very much.
Yeah. Great. And so last but not least, of course, we have Patrick. So again, we are speaking about optimization. And again, I'm sure that Tino Stanković has also a question for you, if I know Tino very well, as I do. Okay, but I can also start with my question. Which is related to the last part of the approach, I would say, because after this optimization process, you perform the voxelization, okay, and then you use this voxelization to tune fill in this design space with lattices. Graded with a graded distribution of lattices. My question is the process ended here or not? Which means, do you need also to validate the model with the lattices, or are you sure that it's gonna work as you have expected?
Thank you for the question. This question is the second part of my work, which is not presented in this paper. It is the validation is also a part. The implant with lattices is re-implanted in the bone, and we are validated with statical FEM analysis and try to check up if our topology optimization from the homogeneous material is matched with the lattice material.
Okay, and are you, for example, maybe I missed this point, but have you also tried to 3D print your implant?
Yes, we try to 3D print our implant with our facilities, and it's printable, but we don't evaluate it on testing machines or so on. So the process is printable, the implant is printable with this lattice, but we didn't evaluate it on testing benches or so on.
Okay. I was curious. And Tino, do you have a question? I saw your hand.
I have several, but I have only time for one, right? so
I'm sorry. Yes.
I have a good question. I think it's a good question. It's about personalized implants in general, right? How do you get away with legislative parts there, right? Once you go to a hospital and say, I will develop a personalized implant, right? These have to be certified, right? And what is currently on the market, you usually have implants that are defined, and then the surgeons would manually bend them, right? For instance, like bone plate and stuff, right? But what about a completely new design, right? Because you also have lattice structure. So how is this challenging? Because I know it's a difficult topic, right? So how would you actually solve that problem, which is fun?
Yes, we know that the barriers are extremely high in the medical approach. So we are working together with veterinaries, where the barriers might be a little bit lower, and we can try to check something. And yes, we are working in a project together where we individualized and try to use letter samples for sheeps, but it's also not finished and not finished yet. And we hope that it will start at the end of the year.
Yeah, because if I just may add, I mean, liability is the problem, right? Because and with the load cases are also the problem, right? Because different person, different story, right? You don't know what you're actually doing, and then you have somehow to consider the problems from such point of view that you satisfy possibilities that are unknown with respect to what is the background of the person, such that it always works, right? And that's the legal point of view, right? So usually they have a solution that works for most of people, right? And everyone is happy, but then we say we are not happy. I want to personalize medicine, and then the problem starts because there are not enough data describing certain elements. But also, I would maybe a good point, since you are doing the joinery, right? Joints and stuff. Check the work from Amir Zatpour in Delft, because he did a lot on exactly what you have shown there, right?
Okay, so can you repeat the name?
It's Amir. Maybe
Zatpour from TU Delft. Actually, yeah, he also tried to use auxeti structures, if I'm not wrong. Yes,
exactly. And he does a lot on implant design, especially the types you have shown right there.
Yes.
All right.
Cool.
Okay.
I think we're done. We would chat now after this, but you can't, right?
So thank you very much to all of you, because it was a very interesting discussion. As you have seen, there were many commonalities among these papers, whether related to the topic or the context, because we had two papers related to the biomedical field somehow. And I want to close with a question to all of you, a general question. And I pick up the idea from Tino comments in the previous sessions. Because Tino, in your previous session, you mentioned related to a paper, I don't remember exactly that paper, but about the fact that you said at a certain point, are we able to consider this technology, hand technology, as a standard manufacturing technology? Or every time we need to start from scratch? And if I may comment on this, the point is that now we are at an historical period where there is an explosion of stuff. Some of them are really, I would say, really reliable. Other a little bit less, probably because they are a little bit breakthrough, I would say. So I know that this makes our life very complex, the life of Giovanni, the life of Adam very complex, and so on. But maybe there are plenty of opportunities. And what do you think? Is a closing question, I would say, Tino, or the other. Can you comment?
Of course, I agree with you, right? It's for us, it's very nice, right? Because it opened multitude of possibilities and things to do and try out, right? Which is always nice for researchers, right? And now designers alike, right? Because things are changing, right? And you can actually make an impact.
Yeah. Right? And Adam, you need to suggest us the right infrastructures that we need, of course, thanks to your research.
Yes. And I would say keep a look at a project called DDAM that is sort of hosted by Chalmers. It's a large project, and Professor Ola Isaksson is the sort of project manager for that. And I guess you're familiar with him.
Yes.
Saw you on Monday, I think. There are several use cases there. So this is not, of course, only for this type of use case, but there we also look into IP protection, where a company wants to have external print hubs, other type of issues, but also related to the digital infrastructure. Another case where they want to do remanufacturing, another type of complexity, but also issues with the same. So I think this topic is close to the industrialization. It's more from a company perspective, because also relating to your question, I think from a research point of view, I guess the technology is already there in terms of being ready to use. And I think the experience I see now, I'm only 1 year into my PhD, so I'm perhaps don't have that much experience, but what I see within the company is that they are currently trying to understand what is the best use of AI. So not really whether they would use it, but rather how it can be utilized in industry.
Okay, so I think we reached the end of the session. Thank you very much once again for all your contribution or your feedback, your insight and reflection on this topic. There is still a lot of work to do, but it is very good because it means we have many possibilities also for the next year to meet each other again during these sessions, which is very nice. And of course, please stay tuned, because after this session, there will be another session on design for additive manufacturing, chaired by Professor George Fadel. So I'm sure you will enjoy also this session on additive manufacturing. So once again, thank you very much, and enjoy the rest of the conference. Bye-bye.
Thank you. Bye.
Thank you. Bye.